The remainder of our course deals with inference, where we select a sample from a population and we do calculations on that sample, and then based on the information from the sample, we try to say something or infer something about the population. For example, one of the questions I come back to often is, I'm interested in the average commute distance for Cal Poly Pomona students. How far do students, on average, drive to school? But I don't want to talk to all 25,000 students to get that answer. So perhaps I select a random sample of 200 students and ask those 200 students how far they drive to get to Cal Poly. And then I can find the average for my sample, and that'll be my sample mean. And then based on my sample mean, I can make some prediction about the population mean, the average commute for all students. But the problem is that if I grabbed a different random sample of 200 students, I would get a different sample mean. So there's variability in the value of x bar from one sample to another. And one of the big things we got to learn about in this chapter is what the distribution of those x bars looks like, so that later on, when we get a particular value of x bar from a sample, we'll have some idea how close that x bar is to the population mean. In this chapter, when we're talking about sampling distributions, we're going to talk about shape, center, and spread. And the shape often involves the normal distribution, which is why we're learning about this topic now, after having just mastered the normal distribution. So just to give you a picture view of what it looks like, the sampling distribution of x bar. This is an activity that I would do in class, excuse me, if we were meeting in class. I have this activity where I give students a copy of the Gettysburg Address, and I ask students to pick 5 words at random from the Gettysburg Address. Now, since we're not meeting face-to-face, I'm going to simulate doing this activity. But what I'm trying to simulate here is this. I have this population, which is the words in the Gettysburg Address, and I would like to know the average length of the words in the Gettysburg Address. But instead of examining all of the words in the Gettysburg Address, I'm going to examine a small sample of, to start with, I'm going to examine a small sample of 5 words from the Gettysburg Address. So here's the words in the Gettysburg Address. So I have them numbered from 1 to 273 or something like that, or 271. And then I have each word in the Gettysburg Address, and I have how many letters are in that word. Then in this next item over here, I'm selecting 5 words at random from the Gettysburg Address. And to see what that would look like, I'm going to bring a table over here. So here's 5 words at random from the Gettysburg Address. And there's a different 5 words and a different 5 words and so on. So this is simulating picking 5 words at random from the Gettysburg Address. And then over here, we're going to figure out the mean. It says measures, but we're going to figure out the mean of the 5 words selected from the Gettysburg Address. So to see what that looks like, we have this. So that mean for my sample is referred to as x bar. And if I get a different random sample of 5 words, I get a different average word length. And every time I grab a different sample of 5 words, I get a different sample mean. And I could also do a graph of those X bars, do a graph of the sample means. And then we could continue. I only have 5 sample means thus far, so let me get another 25. And you see points are being added to my dot plot. So I've got 30 X bars right now, and this is what the graph would look like if we were doing this in class and we had about 30 people in class, each person selecting 5 words at random from the Gettysburg Address and then calculating the X bar for their sample. But I want to do this a lot more times, and to speed this up, I'm going to turn off the animation. Let me just make sure my animation is turned off here as well. Okay. So now I've got 100 X bars, and we're starting to see the distribution of these X bars take shape. That's 100. Let me do 400 more. So that'll give us 500 X bars. And so this is what we're talking about when we refer to the sampling distribution of X bar. If we were to sample repeatedly from the population and calculate X bar for each of our samples, we would get a whole bunch of different X bars. And what would the distribution of those X bars look like? So that's what we're studying, is the distribution of X bars. Okay, so first thing we want to talk about is the center. So it turns out that as long as you have a simple random sample, the mean of the X bars is the population mean. So if we look back over here at this distribution of X bars, the center of those X bars should be the population mean. So a couple things here. Okay, so just to drag this into here, the average of our population is 4.24 roughly. And let me add the standard deviation in there. Summary, add basic statistics. So our mean, this is for the population, our mean is 4.24 and our standard deviation is 2.11. Okay, so if I come over here and look at the X bars, this is kind of interesting. For the distribution of our X bars, and let me also add basic statistics here. So the mean of our X bars should be 4.24, just like it is for the population mean. And the only reason why it's not is because 500 is not a lot of X bars. So if I jack this up to, let's say we do another 2,000 X bars, that'll give us 2,500 X bars, which is still not a lot, but it's better than 500. So when the simulation is done, this list in the background over here will have 2,500 values of X bar, and our dot plot here will have 2,500 dots. Just a few more seconds for the simulation to finish. Okay, so now that I've gotten substantially more X bars, you can see the shape of our distribution of X bars looks very similar over here. But now the mean of all of those X bars is 4.21. And if we could do every possible X bar, if we could do every possible sample of size 5 and list all of those X bars, the mean of all those X bars would be the population mean. That's what this formula here is trying to say. The mean of all possible x bars is the population mean mu. So a much simpler example of that, so that we can actually do some calculations. Suppose I just had a population consisting of the numbers 1, 2, and 6. It's pretty easy to figure out the population mean, add those numbers together and divide by 3. That gives you a population mean of 3. Now, from this population, which is only 3 numbers, let's take samples of size 2 with replacement. These are all the possible samples of size 2 that we could get. Okay, so now there's only 9 possible samples I can get. So it's easy enough to figure out the mean of each of those samples. If my sample is the number 1 and the number 1, then the sample mean is 1. If my sample is a 1 followed by a 2, then the sample mean is 1.5, and so on. So this next calculation will give a little bit more meaning to, I'm trying to shed some light on this formula here that says the mean of the x bars is the population mean. Here's all the possible x bars. So to find the mean of the x bars, mu subscript x bar, you would add all those x bars together and divide by 9, which gives you 27 divided by 9, which is 3, which is exactly the population mean. So the average of all of the x bars is just the population mean. That should always happen. What's particularly interesting to me about this is none of our x bars was equal to 3, but yet the average of all the x bars is 3. So that's the meaning of the formula. The mean of the x bars is the population mean, or mu subscript x bar is mu. Now, the next topic is spread. So the standard deviation of the x bars is the standard deviation of the population divided by radical n. So how far spread out the x bars are is partly due to how far spread out the population is, but it's also partly due to the sample size. And what's really important about this formula is, as the sample size increases, the spread of the x bars decreases. So let me show you an example of this from the simulation, but this is a simulation that I've already done here. So this is our population of words in the Gettysburg Address. Some words have a length of only 1 letter, and some words have a length of 11 letters. If we grab samples of size 2, this is what the distribution of x bars looks like. Notice the x bar values go from here to here. They're a little bit less spread out than the population is. All of these graphs have a number line that goes from 0 to 12. If the sample size is 5, then the distribution of x bars looks like this. All of the x bars are between roughly 2 and 8. If the sample size, if this document will scroll, if the sample size is 40, now the x bars are much more tightly bunched, and pretty much all of the x bars are between 3-ish and 5-ish. So the point is that as the sample size gets bigger, in this case it's 40, when the sample size gets bigger, the spread of the x bars gets smaller. Sample size of 150, now all of the x bars are pretty much between about 3.8 and about 4.8. So the x bars are becoming much more tightly bunched, which is good news if you're trying to estimate the population mean, because now all of the x bars are pretty dang close to the population mean. And to take it to a little bit more extreme level, if your sample size is 1,000, now all of the x bars are between about 4 and about 4.5. So all of the x bars are extremely close to the population mean. Again, the point is with these series of pictures is that as the sample size gets bigger, as the sample size gets bigger, the spread of the x bars gets smaller. The x bars get closer and closer to one another. Do a numerical example showing that that works. For our numbers, for our population of our small population of 1, 2, and 6, just 3 numbers. We already figured out that the population mean is 3. We can figure out the population standard deviation is 2.16. So according to this formula for standard deviation, the standard deviation of the x bars should be the standard deviation of the population, 2.16, divided by radical 2, because 2 is our sample size. So the standard deviation of our x bars should be 1.527. But we have a list up here somewhere. We have a list of all the possible x bars. So we can actually just figure out the standard deviation of those x bars. And when we find out the standard deviation of those x bars, sure enough, it turns out to be 1.527, which is exactly what it should be according to the formula. So this just proves that the formula works in this one particular case. If we were all stat majors, then we would go through all the mathiness of proving that this is always the case, that this formula always holds. Now, the one small wrinkle here is that the formula sigma subscript x bar equals sigma over radical n, that formula is always true if you're sampling with replacement. But if you're not sampling with replacement, then we have a somewhat uglier formula to use, which is the same formula that we have up here, except with this extra radical tacked on at the end. So back to our example of our population of just 1, 2, and 6. If we were not sampling with replacement, then we wouldn't be able to get the same number twice. So now there's only 6 possible samples we could get, which results in these 6 values of x bar. Now the mean of the x bars, there's only 6 x bars now, but the mean of the x bars is still the population mean. That doesn't change. But look at the standard deviation of the x bars. The standard deviation of these 6 x bars turns out to be 1.08. Remember before it was 1.52. So why is it 1.08? It's because it's following this uglier formula with this extra radical at the end. So it's the population standard deviation divided by radical n, and then this extra radical, population size minus the sample size over the population size minus 1. So most books say that you can use the simpler version of the standard deviation formula as long as the population is large compared to the sample, or conversely, the sample is small compared to the population. The reason for that is if the population is 10 times larger than the sample, then this radical is 0.95. And if the population is 20 times larger than the sample, then this radical is about 0.98. And the point is that this radical gets closer and closer to 1 as the population becomes really large compared to the sample. So many authors reason that if this radical is close to 1, then you can just leave off the radical and go with the more simple formula. So usually the guideline is you can use this simpler formula for the standard deviation if you're sampling with replacement, or if the sample is small compared to the population. So now let's talk about shape. When the population from which we're sampling is normal, the shape of the distribution of x bar will be normal regardless of the sample size. So let me show you an illustration of that. So here we have a population which is normal, happens to have a mean of 16 and a standard deviation of 5, but that's kind of irrelevant at this point. We have a population that is normal. And now I'm going to grab samples of size 2, So there's 2 items selected at random from the population. Those 2 items have this mean. So there's a graph of our x bar. And there's another x bar, and another x bar, and so on. And after doing tens of thousands of x bars, notice that the distribution of the x bars looks very normal. This will always happen if the population is normal. Also notice that the mean of our population is 16 and the mean of our x bars is 16, just as expected according to the first formula we learned about sampling distributions. Also look at the standard deviation. The standard deviation of our x bars is 3.53. That's because the standard deviation of our population is 5. Let me do this. 5 divided by radical 2. 3.53 or 3.54, which is exactly what we're getting here for the standard deviation of the x bars. So the point is that even with a small sample size like 2, by the way, I don't like that this app uses capital N instead of lowercase n, but even for a sample size of only 2, the distribution of x bars will look normal if the population is normal. However, when the population from which we're sampling is not normal and the sample size is small, the shape of the distribution of x bars will resemble the shape of the population. So for example, if our population is skewed and our sample size is only 2, then the distribution of x bars will also be skewed. Now notice the other 2 formulas are still working. The mean of the population is 8.08. The mean of our x bars is about 8.08. The standard deviation of the population is 622, and 6.22 divided by radical n is 4.39, basically 4.4. And so the standard deviation of our x bars is 4.4. So those 2 formulas are still working, but because the population is skewed to the right, the distribution of x bars is also skewed to the right. So that kind of kills us if we're attempting to use the normal distribution. But here's one of the most beautiful things in statistics. As the sample size increases, the shape of the distribution of x bars looks more normal. If we go back to this app and we grab samples of size 10, notice there's a little tiny bit of a tail over here, but this is looking much more symmetric, even with the sample size of only 10. So the population that I'm sampling from is badly skewed to the right, but the distribution of x bars is still very symmetric, even for a sample size of 10. If we jack it up higher to a sample size of 25, you can't get much more symmetric than that. That is very nicely symmetric. Also notice that the mean of the population is 8.08. The mean of my x bars is 8.08. The standard deviation of the population is 6.22. The standard deviation of my x bars is 1.25. Why? Because the standard deviation of the population is 6.22. 1.24. Standard deviation of the x bars is 1.24. But the big deal here is that as the sample size gets bigger, the distribution of x bars looks normal, even if the population is skewed or the population is not normal. That's a very important result in statistics known as the central limit theorem. As the sample size approaches infinity, the distribution of x bars approaches normality. And even if I do something, even if the population is really strange looking, like maybe let's say something like this. Okay, if your sample size is small, the distribution of your x bars is going to kind of resemble the population distribution. But if your sample size is large, the distribution of x bars is going to look normal. And a long time ago, somewhere along the line, statisticians decided that quote-unquote large would be a sample size of at least 30. So if we put all this together, the mean of the x bars is the population mean. The standard deviation of the x bars is the standard deviation of the population divided by radical n. And the shape of the x bars is approximately normal if your population is normal or if the sample size is greater than or equal to 30, according to the central limit theorem. Now, a couple other loose ends here. Since the sampling distribution is often normal or approximately normal, let's remember how we calculated z-scores. In the past chapter, we calculated z-scores like this. But in this chapter, since we're going to be turning a value of x bar into a z-score, then we need to turn an x bar into a z-score by subtracting the mean of the x bars and divided by the standard deviation of the x bars. And according to the formulas that we just reviewed up here, the mean of the x bars is the population mean. So the mean of the x bars is the population mean, and the standard deviation of the x bars is the standard deviation of the population divided by radical n. So we're going to use that formula for calculating z-scores. So here's a simple example. Suppose the average commute distance for all Cal Poly Pomona students is 12.7 miles, a standard deviation of 8.8 miles. We select a random sample of 200 Cal Poly Pomona students. What is the probability that their average commute is less than 11 miles? So, when the problem says the average commute distance for all Cal Poly Pomona students is 12.7 miles, that's the population mean. So we're going to say that mu is 12.7. When the problem says with a standard deviation of 8.8 miles, that's the population standard deviation, so sigma is 8.8. When the problem says we have a random sample of 200 Cal Poly Pomona students, that means our sample size is 200. When the problem says what is the probability that their average commute, whose average commute? The sample, the average of the sample is less than 11. So that's the probability that x bar is less than 11. So checking the three things that we need to have in place from earlier, we have a random sample, therefore the mean of the x bars is the population mean. The sample is way less than 1/10 of the population. Our sample is 200, and there's 25,000 Cal Poly Pomona students. So therefore the standard deviation of the x bars is the standard deviation of the population divided by radical n. And since our sample size is large meaning greater than 30, then we know the x bars follow a normal distribution, or they're approximately normal. So then we can turn this value of x bar, 11, into a z-score by subtracting the population mean and dividing by the population standard deviation divided by radical 200. So be careful here because you've got a fraction within a fraction. So be careful when you're doing that calculation. And anyways, that gives us a z-score of negative 2.73. So the probability of getting an x bar less than 11 is the probability of getting a z-score less than negative 2.73. And now we go over to our z-score table somewhere. The probability of a z-score less than negative 2.73 is this entry right here, 0032. So there's our probability of 0032. Or if you're using the calculator instead of a table, you can say normal CDF and go from negative infinity to negative 2.73. That should give us the same answer, 0.0032. So that's just, once we have this x bar turned into a z-score, then it's just a matter of looking up the z-score on the table or looking up the z-score on the calculator like we've done in the past. The second part of this question was, what is the probability their average commute is between 11.4 and 11.5 miles? Okay, so now we have two values of x bar to turn into z-scores. So I'm turning the 11.4 into a z-score. I'm turning the 11.5 into a z-score. So the probability that the average commute for our sample, x bar, is between 11.4 and 11.5 is the same as the probability of having a z-score between negative 2.09 and negative 1.93. So I look up those two z-scores on the table for the negative 1.93. For the negative, I gotta scroll down just a little bit. For the negative 1.93, we have this value right here from the table, 0.268. And then when we look up the z-score of negative 2.09, negative 2.09, we get this value from the table. So that's 0.183. Subtract those two, and that's our probability. Or for people using the calculator, you can say normal CDF from a z-score of negative 2.09 to a z-score of negative 1.93. And that's 0.085. Same answer we got before. Let's see how all that would look on one of the homework problems. So I have a homework problem here. It says Young's modulus is a quantitative measure of stiffness. Suppose that the mean, population mean, is 70 and the standard deviation is 2.1. And suppose that this distribution is normal. What is the probability that x bar is between 69 and 71? So I'm going to turn 69 and 71 into z-scores. Just a second here. I'm going to turn 69 and 71 into z-scores. So I've got 69 minus 70 divided by the standard deviation over radical n. That gives me a z-score of negative 2.38. And so that's turning 69 into a z-score. Now to turn 70 into a z-score, sorry, not 70, but 71. To turn 71 into a z-score, subtract 70 and divide by the standard deviation over radical n. That's a z-score of positive 2.38. So, using my calculator instead of the table, from negative 2.38 to positive 2.38, that probability is 9827, which is exactly the answer they have right there. Then a slightly different question, they say, what's the probability that the mean diameter is greater than 71 when the sample size is 36? That's really key that they change the sample size for part B. So with a sample size of 36, so I want to go back to this fraction here. I'm turning 71 into a z-score by subtracting 70 and dividing by the standard deviation over radical n. But now my sample size is 36. So this is a z-score of 2.86, let's say, 2.86. So the probability of a z-score greater than 2.86, so I'm going to go from 2.86 to infinity. is 0.0021, which we see is the answer on the answer key right there. By the way, for those of you that are stuck using the table, they have a link right here to the table that you can click on. But if I'm stuck using the table, I look up a z-score of 2.86. So that's going to be on the other side of this table. I look up a z-score. I look up a z-score of 2.86. And this is 0, 1, 2, 3, 4, 5, 6. So that's 9979. And 1 minus 9979 is the same, 0021. So that's everything that you should know about the sampling distribution of X bar. Check out the other video on the sampling distribution of p hat, and that'll help you out with the second half of the homework.